All right, hello everyone. My name is Mason Welch, and today we're going to be talking a little bit about torque on a current loop. And to the uneducated in physics, that probably would mean a bunch of nothing, but to us who have traversed the long and widening road of Physics 106, this probably means a lot more. And it's important to understand this because this concept has really made a big difference in our lives. And it's the basis for electric motors. Because of this um, magnetic torque on a loop, we're able to have things like electric dental handpieces, electric cars, and really most anything with an electric motor runs based on this concept. And so it's very important to understand, and it's a pretty interesting and fun concept to learn as well, I think. And my hope for today is just that I can help you understand it a little bit better and hopefully give you some good thought activities just to think through it and logic our way through why this works. Why are we able to create a motor based on just a wire loop, a magnetic field, and it's some current. And it's pretty interesting stuff. So we're going to start right here. We have our basic wire, and we're going to say that this wire, you see it's in a loop, and we're going to put it on a magnetic field. And as you can see here, those green lines represent the direction of the magnetic field, and the magnetic field is going to the right on this loop. And so on top of that, we're going to add the current that is moving on the loop. Now remember the conventions for currents. The current is always flowing in the direction of wherever the positive charge is going. So if you were tracking electrons, they would be going the opposite of those little blue arrows that we have drawn in. But the basis of this is that your current is going along the blue arrows along that wire, as you can see, coming in and out of that wire, and once again, the magnetic field is going to the right. Now, to start out, I want to consider each one of the sections of this wire as its own entity to figure out what sort of force is being generated, because we know that when there's a current and a magnetic field together, there's going to be a net force on the system. So let's just start out by considering this little spot right here, okay? You have your current is moving to the left and your magnetic field is moving to the right. And the same thing is going on with this section as well. Your current is going to the left, magnetic field to the right. And so I want you to think for just a second, what sort of net force is acting on that area? And the answer is there's no net force. The forces cancel each other out. Now let's consider what happens here at the top of the wire. At the top of the wire, your current and your magnetic field are going in the same direction. So what sort of force is going to exist there? The answer is there's no force at the top because there's no angle between the magnetic field and the current. And as we'll discuss later in an equation, you need to have an angle between those in order for there to be a difference in order for there to be a force. Now let's consider this left side. This left side is a little different because you have your current moving up and your magnetic field moving to the right. Now let's stop and think for a second. How do you find the net force if you have a current and a magnetic field going in a certain direction? How do you find where that net force is going to be? And the answer is the right-hand rule. Now, if you remember the right-hand rule, you're going to be able to put your thumb in the direction of the magnetic field and your fingers pointing in the direction of the current. And if you do that, then the direction that your palm is facing is going to be the direction of the net force. Okay, so using that logic, which direction is the net force here on the left side? And I'd ask you the same question here for the right side. Here you have your current pointing down and your magnetic field pointing to the right. What direction is your net force going to be? Okay, so just take a moment to think about that. And right here, we have the results. As you can see, the net force on the left side is going into the page, and on the right side, it's coming out of the page. All right, so you have these two forces that are going in the opposite direction. So then the next question comes, is there a net force here? Is there, on the whole system, is there going to be a net force? You know, we have these two forces on either side pushing against each other. So the obvious answer should be no. there should be no net force because these are equal and opposite forces. Now, if you logic your way through this and really think about it, you should be able to see that there is going to be some sort of movement, right? And so the next question we need to answer is there going to be a net torque? And based on the title of the video, you should be able to answer yes, there is a net torque. So let's think for a second, how does torque work? If there is a torque, what's going on with it here? If we were to draw an axis, look at this red line going down the middle of the wire. This would be the axis around which this wire loop we're rotating, correct? Because on the right side you have it coming out towards you, left side is going in. So you can imagine it rotating around this axis as fast or as slow as you'd like. And that creates torque. All right, so now let's get into defining a little bit of what's going on here and coming up with some equations. So if you wanted to discover how much torque is going on with this wire loop system, you could find that out. So first things first, we need to define the width and the height. And I have to apologize, these graphics that I'm using don't properly show exactly how tall or how short the wire loop is. But basically from one end to another is going to be the width, as you can see there. And then on the side, you have what would be the length or the height of the wire loop. And these are going to be important values in determining the torque. So our equation for torque is going to be force times distance times the sine of theta. Okay, so let's think through that real quick. Torque is force applied a certain distance. And then obviously you need the sine of theta to account for the angle at which you have those different forces. So in this case, we don't need to worry about the sine of theta because of that activity that we did at the beginning where we were able to nullify the forces at the top and the bottom of the wire because they don't have that necessary angle between them and the magnetic field. So if we ignore sine of theta and make a few other assumptions, we're able to kind of go a little bit deeper into this and consider, okay, what does F mean and what does D mean? What is the force and what is the distance? So let's start out by breaking down what the force is. The force in this case is going to be defined as BI times H. Okay, so the equation is going to be magnetic field strength times current strength, and then you're going to multiply that by H. And it's important to note that the stronger the magnetic field and the stronger the current and the larger the height, those are all going to increase the torque, which makes sense. You know, if you have a stronger magnetic field going on here, you're going to have a lot stronger of a torque, and same with the current that's flowing through it. So the more powerful your current, the more powerful your magnetic field, the more powerful your motor is going to be that you make out of this. And then how do we define D? What is the distance here, right? It's just an arbitrary term, distance. Well, distance specifically in the context of torque is how far is the force that's being applied from the axis of rotation. Now, remember that red line going down the middle, and if we look at W, half of W is going to be the distance from the axis of rotation to either one of the points of force. So you multiply the whole thing by W over 2, and that will account for distance. So right here we have torque equals the magnetic field strength times current strength times height times W over 2. And that's going to be your equation for torque. Now we can take this a little bit farther. If we wanted to find the torque for the whole system, our equation will be a little bit different again. As you can see right here, our torque for the whole system is going to be B times I times H times W. That being the magnetic field times the current strength times the height times the width. If we really think about it, the height times the width, that's going to create the area, right? So the whole area of the loop, giving us that the next part of the equation, which is B times I times A, and then furthering that idea, sorry, I just had a little distraction in here. The general convention in which it's written would be IAB. So once again, this is an important concept because this torque around this loop, you know, it's not I hope that today we've been able to establish it's not a super crazy difficult concept. You know, if you break it down in its parts, it's actually quite simple to understand. And that the players in this equation are really relatively simple, quite elementary, but the ramifications of this are indeed very big. It's important for us to understand how these motors work, and how it is that we're able to use an electric motor as an alternate to other forms of electricity. And that's all. I hope you've enjoyed this video, and I hope that you will share it with your friends, and I hope it's been informative for you. Have a nice day.